But partial f partial x is f prime of z, right? Excuse me, partial f partial z bar is this, and that's equal to 0 if and only if what? If only this plus this is 0. But that's exactly the Cauchy-Riemann equations, right? Partial f partial x is minus partial f partial y. I times partial f partial y. That being 0 is the Cauchy-Riemann equations. So that's one thing. And then if it's holomorphic, well then f prime of z is partial f partial x, which you could rewrite as this, which is that, because we can replace this with minus I partial f partial y. Then definition of the Wirtinger derivative is that is partial f partial z. So this is, I think, very satisfying, at least in my view. When your function is just a function of z, the derivative with respect to z is equal to the partial derivative with respect to z. We do this kind of thing in calculus 3 when you have a function of several variables and you find out it only depends on one variable, then the partial derivative becomes a total derivative. Like, it's that kind of notational synthesis. Yep.
Is there a way to decompose any function into like holomorphic and anti-holomorphic parts? Sort of like
Yeah, I think so. Because x and y, think about this, x and y have what? X is equal to what? X is equal to, well, it's the real part of z. Yes, that's true, but unhelpful. So x is equal to 1/2 of z plus z bar. What's y equal to? Y is equal to 1/2i of z minus z bar. So those formulas mean if I have a function of x and y, I can take x, replace it with 1/2 z plus z bar. I can take y and replace it with 1/2i z minus z bar. So yes, any function of x and y can be converted to explicitly a function of z and z bar. That's right. So in that sense, really z and z bar, it's a notation for another pair of real variables, but it's a complex notation for a pair of independent real variables. That's what's going on, truth be told. But let's stop and smell the roses here for a second. Suppose you want to show that is tangent of z plus z squared plus z cubed, is this complex differentiable? So first of all, let's not even talk about the limiting approach, right? Definitely not. No. No, sir. How about the Cauchy-Riemann approach?
also
We'd have to calculate the component functions, right? The u and the v. We'd have to show that ux is equal to vy and that vx is equal to minus uy. Like, whoa, that would be dastardly here, right?
you could just take the Wirtinger derivative.
Right, but with the Wirtinger derivative, partial z bar of secant squared of tangent is actually just secant squared. Now, admittedly, we're using the calculus I haven't quite proved, so, but you'll forgive me. You're like, can we also use that? Yes, if the problem says to do the Wirtinger approach, this is understood. You can do like I did here. Anyway, so derivative of tangent secant squared, and then the chain rule says I have to differentiate the inside part, and nope, that's 0. So the partial derivative with respect to z bar is 0. Therefore, that means the Cauchy-Riemann equations hold for this function. And that function is clearly continuously differentiable because, hey, it's just the composite of a tangent and powers of z. That's just polynomials in x and y. That's clearly continuously differentiable. Therefore, this is a complex differentiable function. That's simple, right? So I think the Wirtinger calculus is worth talking about. All right. The book you guys used last semester, like Saff and Snyder, it's relegated to like a homework problem in there, but whatever. Here's another one. If I had the Gaussian function, right, exponential of x squared plus y squared, maybe there should be minus here for it to be Gaussian, but whatever. Well, that's z bar, right? So if you calculate the partial derivative of that, well, we get z exponential z bar, which shows you that this is not holomorphic. But actually, this calculation does also indicate that it is complex differentiable at the origin only. That is true. And this is really what you wanted me to show you, Ben. This is what you were looking for all along, was the fact that if we have a derivative of a function of z at t, there's a kind of chain rule with respect to the z derivative and the partial z bar derivative. So we replace partial derivatives of x and y with partial derivatives of z and z bar. That's not really for today. I'm just humoring you. So I'm going to put it away. Put it away. Put it away. All right, so my apologies for the speed of today, but I don't think, like, I could spend 3 weeks on this, and I could go through every gory detail, but the gory details are in the notes, and I'd like you to understand them, right? But I wanted to leave us much more time for the calculations which matter. So example, what am I on?
4.
Example 4. All right. So now what do we have? We now have the tools that we need to discuss complex differentiability like grown-ups. So let's talk about the differentiability of e to the z. F of z equals e to the z. This is e to the x times cosine y plus I e to the x times the sine of y. All right? Is this complex differentiable? So, see, the problem with me using the Wirtinger calculus at this point is it assumes things we haven't proved. So we'll get, once we do a bunch of these, then we're more justified in that, I guess. But there's an itch there I need to scratch, but I shouldn't do it in class. Anyway,
This time we use the quotient.
yeah, we'll use the standard plain Jane Cauchy-Riemann. Ux is equal to e to the x. The partial derivatives here, you know, and that's vy, right? Because when we differentiate with respect to y, it changes to cosine y, right? On the other hand, if we calculate vx, we get e to the x cosine, oh my bad, e to the x sine y, right? And that's equal to minus uy, because when we take the y derivative, we get the minus sign.
Because derivative of cosine is negative sine.
Okay, so what does this prove?
It is complex differential everywhere.
This yeah, exactly. This proves that the exponential is everywhere complex differentiable. And not just that, right? Because we then have the d dz of e to the z is equal to, well, partial x of e to the z, right? What is that actually formulaically? It's, well, it's ux plus ivx, right? Which is just literally e to the z. Hooray, the derivative of e to the z is e to the z. Yeah.
I don't really understand how you got u sub x equals e to the x cosine. I understand how, well, I don't understand the notation.
What
I
notation?
don't understand how that's equal to b. I don't understand how u sub x becomes
The partial derivative?
to b sub y.
Like-
So that's what that's saying.
But yeah, these are partial derivatives. Yeah.
Okay.
Yeah. Here's another one. How about f of z equals to, oh, that one's gonna, I was about to do something that would have been unpleasant. That was dumb. Let me not do that. So we got a couple different ways we could go here. When you think about sinh, all right, there are 2 different paths we could go down. The one is just to go, oh, well, that's 1/2. That is literally 1/2 e to the z plus, you know, minus rather, e to the minus z, right? So df dz is equal to d dz, I'll bring the half out, e to the z, right? Minus 1/2 d dz of e to the minus z, which then gives me 1/2 e to the z plus e to the minus z. Using the chain rule here, right? There is a chain rule still, for the same reasons as in Calculus 1, and that's Cauchy. Now that's one way we could go, right? What's the other way? The other way would be to look at the component functions here, show that they satisfy the Cauchy-Riemann equations, And that would prove it's complex differentiable, right? Let's, you know what, I showed you z squared. Let's look at it again. Z squared is x squared minus y squared plus 2ixy, right? So for this function, what are the component functions? You got u is x squared minus y squared. You got v is equal to 2xy. Yep.
You also look at the z bar stuff almost like you had changed coordinates.
It's, yeah, maybe there's something to say there, but well, yeah. Well, I've thought a lot about trying to understand the geometry of it, and I've never come to any kind of satisfactory understanding. And I've thought about it a lot.
It's more just an algebraic.
As far as I can cipher, it's just an algebra trick. The same thing come up in my thesis in terms of super coordinates, introducing these things called chiral coordinates. But anyway, so these here are the partial derivatives. That's fine, right? We agree? And do these satisfy the Cauchy-Riemann equations? So we have ux is equal to 2x is equal to vy. We have vx is equal to 2y is equal to minus uy, right? Cauchy-Riemann equations are true. So then, notice this, df dz, right, is equal to partial f partial x, which we can find the formula, if you want, we can just find the formula like this. I mean, yeah, I could just do, of course I could do ux plus ivx, I've already calculated them. But I want to impress on you that when the complex derivative exists, you can calculate it by just extra differentiating. So it's 2x plus 2iy, also known as 2z. And what am I'm always using the fact that these are continuously differentiable. Therefore, Cauchy-Riemann equations holding implies complex differentiability. That theorem we use over and over and over again. So the thing I proved carefully last time matters. That is the, the technical advanced calculus that lies at the heart of everything here. So going forward, what our project is next is to understand what does it really mean for a function to be complex differentiable. Like, I mean, I've given you 4 different ways of defining it today, right? What do these do for us? Why do we care? It's all good. So the first answer to this, do you guys know about Laplace's equation?
Yeah.
What's Laplace's equation?
Gradient squared of u is equal to 0?
I'll make your u of phi equal to 0. Sure, yeah, this is Laplace's equation in the abstract. In the plane, it would look like phi xx plus phi yy equals to 0, right? Try it out. What happens if you twice differentiate this with respect to x? You get that back again, right? What happens when you twice differentiate with respect to y? You get this back again, but with a minus. So that is a solution to Laplace's equation. 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 We could go on. If you have a complex differentiable function, we're going to see that the real and imaginary parts of it are solutions to Laplace's equation, which means we can solve Laplace's equations if we use complex functions. And we can come up with really cool solutions to it. Yep.
If you have one solution to Laplace's equation, could you essentially come up with the whatever conjugate, quote-unquote, solution?
That is a great question. That's what we're doing next class. So you're asking, can I take one harmonic function and find another one such that if I'm given u, can I find a v such that u plus iv is complex differentiable? Indeed, yes. Well, given suitable topological restrictions, yeah.